right, the next thing we're going to take a look at today is 6.2. So 6.2 is addition and subtraction, and then also we're going to do a bit on estimation. All right, so we're going to start with the basic addition and subtraction that you would start with if you were teaching. So this is the level of addition and subtraction third graders are currently working on when my daughter brings it home. They're adding and subtracting items that have the same denominator, right? So if an item has the same denominator and we add them together, all we have to do is just add the tops together. We don't do anything with the denominators. And a real quick picture, just for your own sake, of why that would work is if you were to imagine, and I won't draw a great picture because I don't want to spend the time to do it, but imagine you had a circle and it was divided into, let's do 6 pieces, and you were adding 1/6 plus, let's do 2/6. Just fair, I know it's not simplified, but let's just for picture's sake. Then what you would do is you would say, well, each piece has size 1/6. So 1/6 means 1 piece. And then 2/6 means 2 pieces. And visually you can see exactly why this becomes 3 out of 6, because there are still 6 pieces. I didn't sort of add 6 pieces, but it's individual. Still the 6 pieces. Okay. So that's a visual. And then different denominators work differently. So when you have different denominators, you have to get the denominators to be the same. And there's more than one way to do that. One way to get the denominators to be the same is to simply multiply the denominators together. So we kind of talked a little bit about this idea last time. And this is the definition for addition that your book is using. So what they do is that they actually say, let's multiply the denominators together so the denominators are the same. You multiply along this diagonal, so this becomes AD. You multiply along that diagonal, it becomes BC. And then, of course, at the end, you end up having a simplified submass, right? This is the idea we would go with if we were looking at adding and subtracting with different denominators. And I put a note in here in bright red because I want you to be aware of this if you aren't already. Adding and subtracting fractions is one of the most error-prone places for students when they learn fractions. It's the worst. Because with multiplication, you don't have to worry about common denominator stuff. But with addition and subtraction, you've got this extra layer of stuff to do. You know, we learn addition and subtraction first, but sometimes some books and some curriculums you guys will encounter will actually teach kids to multiply fractions before they teach them to add. Because multiplication is an easier operation on fractions than addition is. Okay? So be aware that that might happen. Your book is using addition and subtraction first, so we're going to go in that order. All right, I need a volunteer. Kayla. We're going to have to start picking volunteers. All right, so Kayla. Somebody's telling Kayla, what are we going to do to add 1/3 and 5/3? Add the top. So what do you get, Kayla, if you add the top? Okay, does she get to leave her answer like that? No. So what is 6 over 3? That's equals to 2. Awesome. Thank you, Kayla. I need another volunteer. See, it wasn't scary. It was just fine. Thank you, Megan.
Feeling all right. Yesterday, that we were on our best behavior, like you told us to be, because we volunteered.
All right. All right, so 1/4 and 5/3, they don't have a common denominator, right? Not right now. So I know there's lots of ways to do it. Let's actually do it with that definition that we had on the previous slide. So what will Megan's new denominator be with that definition? 12. So put an equals, Megan, and make a denominator that's a 12. Okay, put a long line on top for me because I want to see it. Just write the long line. We're going to do something with an addition. Oh, I didn't mean that long. I want something with an addition on top, something added to something else, like from that definition we just did a minute ago. Put a plus sign between there. Okay, in the middle on the top. In the middle on the top. Right here.
Great volunteer.
Examples
of
yes, in the middle of the line. You just stand right here because I'm turning it back over you in a minute.
Okay. Oh, there we go. That works. All right.
Okay. All right. So mirroring the last slide. The last slide had something added to something over the denominator that was multiplied. Okay. So look at your last slide on your sheet of paper. What will go in the first spot before the addition sign? 3, because it's 1 times 3. It's the first diagonal from top down. What will go in the second spot? 20. And then we're going to simplify. 3 plus 20 is 23 over 12. And 23 and 12 don't have any factors in common, correct? So it's perfectly fine to leave it just like that. All right, so 23 over 12, we get to leave it just like that. There's no reason to change it into mixed number form. Now, if we had something like 22 over 12, we would reduce it, but we still wouldn't change it into mixed number form. Make sense? Excellent. All right, now we're going to talk a little about mixed numbers. So mixed numbers are very useful in everyday life. They're not really all that easy to work with mathematically, but we think in them a little bit better. For instance, if you had 2½ cookies, right? It means the same thing as 5 halves, but it would be very awkward to say I had 5 halves cookies. Who would look at you and say, dude, what? That doesn't make any sense. Like, did you just have 1 half and you just kept eating? I mean, I don't know. 5 halves is a weird way of saying it. However, from a mathematical perspective, 5 over 2 is an easier number to work with. So we often will use it in our mathematics to work with it. But 2½ makes more sense conceptually. So the first thing we're going to do is we're going to talk about how we change numbers between forms. And the reason we need to is because, as we said, some of them make more sense to talk about and others make more sense to work operations with mathematically. So how would I change 14 over 3 into a mixed number? Divide. Somebody want to put divide for me on the board? It's not scary. Unless you confuse the number. Does it make me pick on somebody? I'll do. Thank you. All right, so just do division like you would with long division, 14 over 3. Yep, just like that. Me too there. Just go ahead and put R2 for now. We'll be fine. Yeah. Okay, so the first thing you do, go ahead and put your pen down here, awesome. So thank you. The first thing you do is you do the division. And when you're working with this, I really want to see the division. Okay, so don't grab your calculator and do it. That's defeating the point. Show me this little step of division. It doesn't take very long. You guys know how to do it. Now then, what you want to do is actually write that as a mixed number. So the first part is the 4. The remainder is a 2. Adding the original 3 that you had as a denominator. So the denominator does not change. The whole number part, the quotient part, is what came out as division. The remainder part becomes the numerator of the next fraction. So then we remember how to change mixed numbers back into fractions and proper fractions. Right, and a visual might be helpful to some of your students. So one of the visuals I saw when I was doing observations of student teaching is that someone had done something like this. So what we do is we multiply 3 times 8, ignore the negative on the answer for now. The negative will just be part of the answer. And then they added it to the 5. So do a visual. Visuals are great. A lot of people learn by seeing. Okay? So 3 times 8 is 24 plus 5 is 29. So we end up with 29. Again, the denominator stays the same, so it's an 8. And the value is negative to start with, so it's negative 10 as well. Remember this? Not too bad, right? All right. A couple of properties. So we worked on properties in Math 1 if you took that one already. There are some properties that get sort of extended into rational numbers, which is what we're working with. One of them is the additive inverse property. We've seen an inverse property for addition before. So this is just an extension. So we're saying if we have a number a over b, then there exists a number of negative a over b. So when we add them together, we get 0. Okay, so for every fraction, or whole number, or natural number, whatever, there's the negation of it. So when you add them together, you get 0. All right, the second one is addition property of equality. You used this all over the place when you were in algebra courses. Right? This is the idea that if I add something to both sides of the equation, or subtract something from both sides of the equation, then the equation still remains equal. Okay? So you're imagining sort of like a balance, a scale balance. And as long as I put a 5-pound weight over here and a 5-pound weight over here, I'm not going to go lopsided. Right? Like working out at a rock. Okay, so don't use a 5-pound weight here and a 20-pound weight here, or something weird going to happen. And I'm probably going to fall over. Okay, so you just do the same amount on both sides. So that's addition, property, and equality. Both of these properties are used extensively for solving equations. And here's an equation. Now, I bring up this equation because there are two ways to solve this equation. You may or may not have seen both of these ways, and you may or may not like both of them. That's okay. Just like we've talked about before, you need to know options because your students think differently than you sometimes. And it's a shock. You had no idea, right? You thought everybody thought like you did. You don't. All right. So let me show you a couple of ways. There's one method. Let me ask you, what method do you remember? If you were solving this problem, what would you do? Okay. So Kayla's approach is what I'm going to call the mixed number approach. Okay? So Kayla wants to take the x minus 2 and 1/2, which equals 3 1/3, and actually add 2 and 1/2 to the other side. Now, following along with what Kayla is suggesting, I'm going to keep them in mixed numbers, which may or may not have been what she was here at next. We're going to do it this way with this option. How can I add 3 1/3 and 2 1/2 together when they're still in mixed number form? Well, one way to do it is kind of like what you do when you add numbers and you do carrying. It's kind of like that, okay? So you add portions together that match. So 2 plus 3 is 5. And then just for a moment, I'm going to write 1/3 plus 1/2 on the right-hand side of that. I have x on the left. 1/3 and 1/2 don't have common denominators, but could they? Sure, we can do it like we had up on the board when Megan was doing her example. So what would the common denominator be? 6. If I multiply here, I get 2, and here I get 3. What does x end up equaling? 5 and 5, 6. So, mixed number approach that we did, I never learned that. Ever did. Okay? Never learned that, and I think it's great. Definitely my favorite approach. I'm going to show you the other approach one that I did learn in school. Both of these are taught, which is why you need to know them. Does anybody know another approach? Yes. Method 2 is an improper fraction approach. All right, so method 2 takes x minus 2 and 1/2 equals 3 1/3. And in some sense, it starts out the same. We're going to put the 2 1/2 on the other side. The difference is going to be how we combine those two numbers. So instead of actually having 2 1/2 and 3 1/3, we're going to actually change those individually into improper fractions. So if I multiply around, multiply and then add, what does 3 1/3 become as an improper fraction? 10/3. And then we do the same thing with the 2 1/2, multiply and then add, and it becomes what? 5/2. We could keep doing what we did on the same problem before, right? It's the same process. I've got different denominators and whatever. So the new denominator would be 6. But my crosses are different. Now I've got 10 times 2, which is, and I've got 5 times 3, which is 15. So this, if I added it together, would be 35 over 6. And here's the point where I'm going to tell you you can't make this 35 over 6. And here's why. How does the problem start? Fixed numbers. So how does the problem end? Fixed numbers. Okay. So that's the only situation under which you need to turn something back into a mixed number. If it started out that way, it needs to end that way. All right, so if we take the 35 over 6 and we do what I asked Marissa to do a minute ago, how many times will 6 go into 35? 5. 5 times 6 is 30. Got a remainder of 5. So this ends up being 5 from here. and then 5/6. Clearly, we got the same answer, but that should be true. We didn't, we should be concerned. There's two very different approaches to doing it. Okay? All right, definition of subtraction looks almost the same as before. We sort of even skipped over the idea of having common denominators, but these are non-common denominators, right? D and D. And, oh, I'm sorry, I'm ahead of where I am. Let me stick where I am. All right, so definition of subtraction that this one's referring to is talking about what it means to subtract, as in visually what it means to subtract. And we did this back in Math 1 as well when we talked about subtraction. If you have A over B and you're subtracting C over D, then what you're actually asking yourself is how much would I have to add to C over D to get back to A over B? And you did this, you've done it before in other classes as well. But all that subtraction is, let me think about some numbers so I can make work. If you did 10 minus 3, one way of thinking about this is saying, what do I need to add to 3? 3 plus what equals to 10? This is usually how we first describe subtraction anyway. What's missing? What's the missing part? Okay. So the subtraction works the same way for rational numbers as before. And this theorem actually is telling you what subtraction means in terms of addition. So subtracting a C over D is the same thing as adding a negative. You guys know that. Right? Addition of a negative is the same thing as subtraction. All right, this is the subtraction slide I thought I was on. So subtraction then with like denominators and then unlike denominators. This slide looks identical to the addition slide, right? The only difference is the subtraction sign there instead of the addition sign, right? So if they're the same denominator, we just subtract the numerators. If they're different denominators, we do the multiplication of the denominators and the multiplication along the crosses to get the numerator and get these simplified. All right, so here we're going to do an example. This is an interesting one. All right, so Martine bought 8 3/4 yards of fabric. She wants to make a skirt using 1 7/8. Pants using 2 3/8, and a vest using 1 2/3, all in yards. How much fabric will be left over? What are we going to do? A lot of numbers in this one. They're all mixed as well. Okay, so remind me your name? Cicely. Cicely says, how about we add the 3 things that she wants to make together, okay? And then subtract that from how much she actually has at the beginning. Sounds like a good approach. You okay with that? All right, so the amount she has at the beginning was the 8 3/4. And then literally what you're wanting to do is subtract the next 3 things added. So that was 1 7/8, 2 3/8, and 1 2/3. All right, so we could choose 2 approaches, right? We could choose that method 1 or that method 2. Method 1 was the mixed numbers, method 2 was the improper fractions. I don't know about you, but I'm not really interested in doing the problem twice, so let's pick one. Which one would you like to do or see? Which one? Second one, improper fractions. Is your suggestion to go?
Well, it just sits. There's 2 of them with the same denominator.
We'll get that done first. Yeah, we will for sure. You're right. But after that, we're eventually going to have to get the denominator, not all of them. That's never I said.
Oh,
you're right.
Yeah.
Okay, so I'm hearing maybe we want to see the improper fraction approach. Is that one right here? Is that okay? Okay, we'll do that one. All right, so Kayla's suggestion is correct, though. Let's actually combine the ones that have the common denominator first. So if you have 1 7/8 and 2 3/8, what does that give you? 3 10/8. Do we get to leave 10/8? All right, so here's 1 2/3 still. And then 10/8 would be 4 2/8. I'm still not quite where I want to be, but I'm getting closer. Do I get to leave 2/8? Not today. Not tomorrow either. All right, so 4 2/8 is actually 4 1/4. Okay, you don't have to show every single one of the steps. Okay, if you can find that together. But I wanted to show it to you in case you weren't for sure what I was doing to jump across the steps. Is everybody okay to this point? Okay. All right, mixed number approach means that I'm going to change each of these, I'm sorry, mixed number, the improper fraction, I'm going to change each of these into an improper fraction. All right, so 8 times 4 is plus 3, 35 over 4. 4 is 17 fourths. 1 2/3 is 5/3. There's actually one thing we can do before we get them into a denominator. What can we do? We could sort of distribute this negative through so that I have, move over here, 35 over 4 minus 17 fourths, and then minus the 5/3. Don't forget that minus will actually be applied to both pieces if you do this. But that'll actually simplify it really nicely, right? I can combine the two that do match in terms of their denominator, and then I'll only have 2 that I have to consider the common denominator for. So it's 35 minus 17. 18. Oh, it gets better all the time because 18 fourths simplifies to what? 9 halves. All right, now we need to get that common denominator. So what will this look like if I get a common denominator? 6 on bottom, good. What goes on top? 27, and then it's minus 10. All right, so what's 27 minus 10? 17 over 6. Do you get to leave it that way? No, it is the answer though, but we're not going to leave it that way because the problem started out with mixed numbers. And to be honest, it makes more sense. We're talking about yards of fabric, and if you talk to the lady at the counter on the yards of fabric, what? Okay, so 17 over 6, we'll change it back into a mixed number. So 17 goes into 6 how many times? Twice, with a remainder of 5. So this ends up being 2 5/6 yards. Thank you. There are units. They should be in your units. 2 5/6 yards. All right. All right, so the next thing we're going to be taking a look at is a little bit in terms of estimation. So one of the issues about estimation has to do with being able to compare values, okay? And comparing values, we can do it concretely like we did last time, where we actually got common denominators, or we actually cross-multiplied this off a real if the English was greater than. But we saw an example last time as well, where I think Haley said, well, you can just look at them and kind of tell the first one's way bigger than the second one if you estimate. That's kind of where we're headed here, okay? So definitions of less than and greater than. So A over B is less than C over D. If when you subtract the bigger one minus the smaller one, you get a positive number. And you should be saying, well, it's yeah, right? Something is going to be bigger if when you subtract the smaller value, you still end up with something positive. Same thing then on the second part has to do with the symbols being backwards. If C over D is greater than A over B, then A over B is less than C over D. It's just the idea of being able to turn an inequality around. And if I did it with numbers, and we'll just do some whole numbers because it works the same way. 2 is less than 3. We'll say if and only if, just to model what this says, 3 is greater than 2. Right? Yeah, right. Okay, so estimation. There are several different ways of doing estimation. One of them is to estimate with convenient fractions. So these are fractions that are roughly equal to what we're given, but easier to work with. Like 1/2, 1/3, 1/4, 2/3, 3/4, something that's more convenient for you to work with. Sometimes fractions are easy in fourths. I like fourths because it models money really well. Quarters of a dollar. Okay, so when I say 3/4, I think 75 cents. Okay, tenths are really well. Again, for money, dimes. I think in terms of money pretty well because I use it on a regular basis. I think you guys probably do too. So then also, well, there are some other examples too. Let's give the ones that we've got. So Estimate the following fractions. Is your estimate high or low? All right, so I've got 12 over 82. What would be nice for this to be estimated as? It's roughly what? 1/8. In essence, what we're doing is we're changing the 12 into a 10 because it's pretty close, and we're changing the 82 into an 80, and it's pretty close, and 10 over 80 is 1/8. Now, if you want to sit and reason and try and figure out is that smaller or bigger than your original one, that's okay, and you can actually do that. There's plenty of things to think about and processes to work through with that. I'm okay if you grab your calculator and compare the decimals as well. All right with me. So if you did 1 over 8, you would get 0.125. What's 12 over 82? Can you get first with the cursor? All right, 146. Whoops, you said 146. Okay, so we took something that's equivalent to about 0.146 and turned it into a fraction that's equivalent to about 1.125. So is our estimate, the 1 over 8, high or low? It's low. It's a little low. In terms of money, it's not a lot low. It's like 3 pennies low, right? It's vastly off. But it is different. How about 2 over 1,001? 1 over 500. Tell me how you got that, Kayla?
Well, I just did what, half of 1,000.
Okay, so basically you change the 1,001 into, in your mind, that's about 1,000. And 2 over 1,000 is about, well, it's 1 over 500 actually. So, and I should do this. Let me fix this. I did it wrong on both of them. We're doing an equivalence approximation. It's not actually equivalent. These are approximations. All right, sorry about that. All right, so it's 1 over 500, and I don't want you to use your calculators because we only changed one thing. What did we do? We made the denominator smaller. So if you divide by something smaller, does the fraction get smaller or bigger? It gets bigger. This is a high estimate, and you can check with your calculator. I'm not saying you can't. But this one was pretty nice because we only changed one piece. You change the denominator gets smaller, the whole fraction gets bigger. If you change the numerator gets bigger, the whole fraction gets bigger. If you just mess with one piece or the other, it's not too bad. All right, one more problem. You're going to write a story problem for 5 1/4 minus 2 1/3. Okay, so put your teacher hat on. You're in the classroom and you're trying to create a reason why in the world a student would ever need to subtract 5 1/4 minus 2 1/3. Okay? You're answering the question, when will I use this in real life? That's what this is doing. Because students will ask. Okay. So if you're sitting here and saying, yeah, well, can you answer that? Give me an example. What could you do? Why would you ever want to subtract 5 1/4 minus 2 1/3?
Cooking.
Cooking a pie? Okay, so let's do that. Let's do something with cooking. So can they do an example of cooking a pie? All right, so how about, do you want to knead 5 1/4?
Yeah.
Okay.
I think you make
All right, so we need 5 1/4 cups of flour. To make 2 pies. Now what? All right, so that'll work. The first pie, so there must be different pie recipes or something, right? That's what's going on. So the first pie, I'll use the words you did, calls for 2 1/3 cups. Now what? Good. How many cups does the second recipe call for? This is a great example. Keep in mind too, this is a great example for whom? Somebody who likes to bake, right? So it might be a great example for some of your students, and it might not for us. So if they stare at you with this blank expression like I'm never going to cook a pie, again, teacher hat on, you might need to think of something different. So for what you're doing for me, this is great. I don't have a problem with it. But just keep that in mind that sometimes the example that might make most sense based on your interests might not make most sense on the other interests or someone else. Okay? So you might actually have to think specifically if the student is asking you, what kinds of things do I think this student might be interested in that would actually apply here? Maybe they run. Could you do an example of this if somebody's running an amount of time? Sure. So you kind of have to think something like that, right? Just an FYI. All right.